we're going to look at a couple different things about exponential functions today. So this is kind of the whole point of what we've been leading up to this unit, is looking at functions with exponents where our variables are at, okay? So one of the first things that we're going to do here is we're going to write up here at the top, an exponential function is any function in the form f of x is equal to a times b to the power of x. So an exponential function is any function in the form of a times b to the power of x. Okay, so when we look at this, a and b are constants, so they're going to be just numbers, where our variables are going to be in the exponent. Okay, a can't be 0, b is going to be bigger than 0 and not 1. Okay, so a, this number that is in the front here, that is going to be our initial value. Okay, that is also considered our starting point, like where we are starting. And it can also be our y-intercept, okay? And b, so b, that is what is actually being raised to the power of x, okay? So b is our constant ratio. So b is what each step is being multiplied by between each step. And so what we're going to do real quick is we're going to look at a little bit of an example, okay? And we're going to talk about it, and I'm going to kind of sketch out what the graph looks like. And then we're going to look at the pieces of it, okay? So before we do that, though, b, so if b is greater than 1, it means our function is going to be increasing. And if it's increasing, it is considered to be an exponential growth function. But if b is less than 1, it is decreasing. And it is an exponential decay function. And b is made up of 1 plus or minus the rate, where it's the rate of growth or decay. So it can be the rate that a car or that a bank account's value is increasing with interest. It can be the rate at which a car's value is decaying as soon as you drive off the lot, like depreciating. Okay, there's a bunch of different things that can be considered an exponential function. So you do not have to sketch this out to the side, but we are going to kind of go through an example, and you are going to use those calculators to help me out. So if we have an x and y axis here, like I said, you do not have to draw this because I've been putting it on the board all day, but I'm doing this so it'll be in the video. But when we look at this, we have our x-axis and we have our y-axis just like normal. Okay, we're going to look at the function f of x is equal to 5 to the power of x. Okay, now this does not have an a. What is the only value a could be so that when we multiply it by 5, it doesn't change? 1. This is like we have 1 times 5 right there. That's kind of what's technically there. Okay, what I want us to do real quick is I want us to plug in some different things into our calculator and see what we get. So if we plug in 5 to the power of -4, what is that? Okay. 0.00 what? 16. Okay. What if we do 5 to the power of -3?
0.008.
Wait, what?
0.008.
Oh, okay. Okay, what about 5 to the -2?
0.004.
No, 0.4.
Okay. What about 5 to the negative 1?
0.2.
No, this, wait, this, what?
0.2. Okay. What about 5 to the 0 power? 5 to the first power? 5 to the second power? 5 to the third power? Okay. 5 to the fourth power? All right. 5 to the fifth power?
3, 1, 2, 5.
All right. Now, just for funsies, we're going to do one more. 5 to the 13th power. No, 5 to the 12th power.
1, 5, 6, 2, 5.
No.
Nope. To the 12th. It is 144 million.
What?
It's 144 million. Then what?
It's 200.
Oh, 244 million.
140,625.
Yeah, 140,625.
Yep.
All right. So I want us to talk about what this means for our graph. This is kind of a pattern that happens with any exponential function. So our values, okay, if I went over here to where -4 is, it would be just barely above the line. Just a little bit above that. A little bit above that. Till we get to 0, it's going to be at 1. Okay? Then at 1, it's going to go up to 5. Then from 5, it's going to go to 25. And it's going to keep going up pretty steeply. Do y'all agree with that?
Yes.
Okay? That is one of the properties of what happens in an exponential function. It starts off really gradual. And then when it does spike, it doesn't just, it goes very quickly. Like, it goes from 5 to 625 very quickly, right? So that is what makes it an exponential growth, is it's growing very rapidly, very quickly, okay? And if it was an exponential decay, it would be going in the opposite way, like that, okay? Now, the reason I want us to look at what this graph looks like is because there's a part of it that it's hard to understand unless you can visualize it. So as we are looking at these values over here, as these values get more and more negative, what number are they getting really close to?
0.
0. Do you think it's ever going to reach 0? No. Okay. It's going to just keep getting closer and closer. Someone do 5 to the power of -12.
Ooh.
Oh.
Okay, tell me what it is.
4.096 times 10 to the negative 9th power.
Yep. So negative 9th power. So it'd be 0.000000004, whatever else, right? That's a very small number. Okay. As this gets more and more negative, it's going to keep getting smaller and smaller, but it will never actually hit 0. Okay. The reason for that is the exponential function in and of itself will not change signs, okay? And so when that happens, you have your imaginary line that it cannot cross. That line right there is basically an imaginary barrier where if it gets close to it, it will not touch it. Think like the force field from the Hunger Games. Y'all, please stop. Extra conversations. You don't need your computer right now. Close it. Okay? So as it is getting closer and closer to this line, it will never touch it because it can't. Okay? It's like if it tried to touch it, it would get shocked and blow up. Okay? It cannot get close to it. So that line is called an asymptote. Okay? And it is a line that the graph approaches more and more but never touches. So it is a line that the graph approaches but never touches. Well, then you'll probably really like this one. Okay, the way that I kind of remember how to explain an asymptote and what happens with an asymptote. So, has everyone in here seen the movie Finding Nemo?
Yes.
Okay, we are all familiar with the fact that Finding Nemo, the entire movie could have been avoided if he would have took the advice and not touched the, what did they call the boat? The butt. Yeah. In Finding Nemo, he should not have touched the butt. Y'all agree with that?
Yes.
Okay. Now, the word asymptote. What does the first, you don't have to say it. What does the first part of the word asymptote sound like?
Rhymes with grass.
It does. And so,
Wait, it sounds like what?
It rhymes with grass.
oh, okay. But anyways, okay? So, you cannot touch the butt. Okay? Cannot touch the asymptote. Don't touch it. Okay? That is a very silly way of thinking about it, but if you ask me, hey, can I put a point here and it's past the asymptote, I'm going to go, oh, don't touch the butt. That's what I'm going to say, okay? Because we cannot do that. It is a line that this graph cannot cross, okay? And so it's not a real line on the graph like that. You would draw a line. It's like an imaginary line that is there to represent where it cannot cross, okay? You'll past it, it's a problem. Yes, ma'am.
Is there like a reason, or is it just like?
So whenever we have especially in the case of exponential functions, okay? So the exponential function, without us doing anything to it, it doesn't matter what number we put there, it's never going to flip to a negative. So it can't become negative, okay? And so because of that, that is where that imaginary line falls. Now, some things get asymptotes because you can't divide by 0. And so those would get an asymptote where you would divide by 0 because that's something you can't do. Basically, it goes where it's going to cause the graph to no longer be able to exist there. After this point, the graph cannot exist, okay? And so that's kind of what it's telling us. It's just telling us where the graph naturally can't be. And so, like, when it is just in the normal state, it can't go past 0, okay? Whenever some things happen to the graph can be shifted up or down. Y'all remember how we had those transformations that just moved the whole graph up or down? If that happens, it can change where our asymptote's located and, like, scoot it down or up. But still, it cannot pass where that asymptote is located, okay? It can never touch the butt, okay? And so that is why it's super important, and I like to emphasize what the asymptote is and why you can't touch it, okay? And that usually gets a chuckle out of at least me. So, and I always like seeing who the one person is in the class that screams out the word. All right. Now, we're going to look at question number 1. Okay, so for question number 1, we are going to write the written form of the function, okay? And so what we're going to do is, in order to write it, we have to know 2 things. We have to know what our initial value is, which that is our A, and we also have to know our constant ratio. Which is our B. So those are the 2 things we need to write the function for an exponential function. So we're going to start by looking at it. So in this table over here, it will almost always give us our y-intercept. Okay? That is where x is 0 and what y is. That y-intercept is what we consider to be our initial value. That's our starting point. That is our A. So our A in this case will be, what is our y value there?
4.
Okay, so that is our A. That is our initial value. Find your y-intercept. Use the y value as your A. Okay, now, to find your constant ratio, okay, the constant ratio is what is being multiplied into by each step to get to the next value, okay? So this one, we can do it pretty easily. 4 times what gives you 12? 12 times what gives you 36? 36 times what gives you 108? 108 times what gives you 324? Okay? This one's pretty easy to see. Okay? Sometimes it won't be as easy to see because maybe it won't be a perfect whole number. It might just be like, it might be a decimal or something like that. Okay, so the way that you can always find your constant ratio is if you take the step below and the step above it, so 12 and divide it by 4. That will give you our constant ratio of 3. If you do 36 divided by 12, that will give us a constant ratio of 3. If you do y'all get what's happening here? You do not have to do all of them. You just want to confirm that it's consistent throughout. Okay? Once you find it, I would double check some of the bigger ones just to make sure it stays the same throughout, because otherwise it's not an exponential function. It has to be the same through everything or it's not an exponential function at all. And so our constant ratio is 3. So we're good to write the function. So we do f of x is equal to our a times b to the power of x. And that is all we have to do to write out the function. Find the starting point, find the ratio, we're good to go. Now, we're also going to look at what happens when we're given a graph. Can we write the equation from it? And we can. We pretty much do the exact same thing we're just doing. So we're still looking for the same things. So we're still finding our initial value. So if I look at this graph, where is our y-intercept on this graph? 120. Okay? That right there is our a. That is our starting value. Okay? Now, from here, we need to find the rest of our points so that we're able to even see what's happening between them. So at 0, the point is 120. At 1, what's the point? 60. At 2, what's the point?
30.
At 3, roughly, what's the point?
15.
Okay, at 4, roughly, what's the point?
7.
Something like that, right? So it goes from 60 divided by 120. What does that give us? It's not 2. 0.5 or 1/2. Okay, so same thing here. It goes from 30 divided by 60, which gives us 1/2. It is very important that you divide it in the order that it's going up. So like the point at 2 divided by the point at 1, because it can mess up your numbers. Because you have to know that 120 is 2 times 60, but we're going from 120 to 160. So we're going down by 1/2. We're getting cut in half each time. So our constant ratio is what? It is 1/2. So our b is 1/2. And now we're good to write our function. So we're going to have f of x is equal to our a times our b to the power of x. You could also write it with parentheses, however you would like. Okay, so that's how we find the equation. So now we're going to take the equation, make a table, and graph it. Okay, so I want us to go ahead and look at page, whatever the next page is, 7? Okay, and we're going to look at a few of these together and then some on our own as well. So when we look at question 3, so we have the function y is equal to 2 to the power of x. So first, before we even start one of these problems, we can decide what if it's growth or decay and what our asymptote is going to be. Okay? So does this equation right here have an a? No. So a is understood to be what? 1. What is our b? 2. So is 2 greater than 1 or less than 1? Greater than 1. If it is greater than 1, automatically that tells us it's going to be a growth function. So it's going to increase from left to right. Okay? Our graph will somehow look like that. We don't know exactly yet, but that's what it will be. Now, is anything being added or subtracted at the end of this graph to move it up or down? No. So as long as nothing is happening to move this function, our asymptote is going to be at y equals 0. So that is, our asymptote will be the imaginary line that runs across the x-axis. So it cannot touch it. That is where it cannot touch. Now, we're going to look at a table of values to do this, okay? I'm going to show you 2 different ways we can do the table of values, okay? So first, okay, we are going to look at all of these tables of values from -2 to 2. The reason we're doing that is that gives us a pretty good picture of what is happening for the whole graph to let us sketch it out, okay? So if you want to just go the plug-in route, you take your function and you go 2 to the power of -2. What is 2 to the power of -2? It is 1/4, because it's technically 1 over 2 squared, which is 1/4, which is the same thing as 0.25. I will say this. People tend to graph easier with the decimal form than the fractional form. It's easier for some people to understand where 0.25 is more than 1/4. You do whatever makes the most sense to you. I'm good with fractions or decimals there. Okay, what about 2 to the power of -1? What is that? 0.5 or 1/2. Either way works. Okay. What is 2 to the power of 0? What is 2 to the power of 1? What is 2 to the power of 2? Okay, so all we did here was just plug them in, right? So now we are good to put these points on our graph. So at -2, I can point a point at about 0.25. It does not have to be perfect. I do not expect you to make these perfect. Then at -1, we can put 1 at 0.5. At 0, we put 1 at 1. 1, we go all the way up to 2. At 2, we go up to 4. And now we have here what our graph looked like. Should my graph ever touch the x-axis? No. Because the x-axis is what in this case? The asymptote. We do not touch it. Okay? So that is our graph. Was that the done? No.
Yes.
Yeah. It's fine. It happens. All right. Now, domain. Okay, remember, domain is your x values. So we look left and right. Does this graph ever stop going to the left? Does this graph ever stop going to the right? No. So what is the domain? Negative infinity to positive infinity, all real numbers. Okay, range. Okay, range is our y values from bottom to top. Where is the lowest this graph can go but not touch? 0. And it goes up to infinity. Now, because it cannot touch the asymptote, will it be a parentheses or a bracket? Parentheses. Okay, then where is the y-intercept? What's the point of the y-intercept? The point, the whole point. 0, 1. There we go. That is all we have to do to graph it. Okay. So now we're going to do number 4. And while we do number 4, we're going to use our calculators to make the table. Okay. So you can do it with either type of calculator. I will quickly walk us through both. I don't care which one you use. For both of these, give you the same thing. But you need how to do it on both. All right, for number 4, okay, we're doing the same thing, okay, but for number 4, what is our b that we're looking at? 1/4. So is that going to be growth or decay? Decay, because it is less than 1. And where will our asymptote be located? 0. Okay, as long as nothing is being added or subtracted to the end, that is where our asymptote goes. Okay, the only time the asymptote moves is if the whole graph moves up or down. Now, we will walk through how to do this on each type of calculator. Okay, so if you have a graphing calculator in front of you, okay, do you see the y equals button? Hit that button. When you hit the y equals button, Okay, you should see this screen here when you hit that y equals button. Is that what y'all see? All right, you are going to type in the equation right there. If something is already typed there, just clear it out. Okay, so we're gonna do parentheses 1/4 to the power of x. Is that the equation? All right, now, if you pressed graph, it's going to graph it for you. Super great, except I can't really read those points very well. So what you can do is you can press second graph. Do y'all see where it says table in blue? So we do second graph to get the table. And look, it gives us every single table value for this entire function. Okay, so we can use that to fill in from -2 to 2.
Wait, go through that entire thing.
Okay, so you hit y equals, you type in your function. So y equals, type in your function. Okay, then you press, you don't do the letter X, you use the variable button, which is right here. So you do parentheses, you use alpha x to get the fraction, type in 1/4, then you use the up arrow to make a exponent, and then you use the x variable key right there. Okay, once you do that and have it all typed in, type it in exactly like it's written on your paper. Exactly, okay? Then you will do second graph, and it will give you the full table. And if you scroll up or down, it gives you every single value in there. Okay? And so we can use this full table to do all of those things. Okay? So now we're going to use that table to write in our values. Okay? So at -2, our table gives us what y value? At -1, our table gives us what y value? At 0, it gives us what y value? At 1, it gives us what y value? Okay, at 2, what y value does it give us? 1/16. Now, we are good to graph that. Now, you can also write those as decimals. If you wanted to say that is 0.25, and that is, and then to get out of that on your calculator, you just press graph clear. And that is 0.0625, okay? So now, we're good to graph it. So can I graph the point -2, 16 on there?
No.
It doesn't quite fit. So I just go to the next one. -1/4, I can graph it. 0, 1, I can graph. 1, 1/4, I can graph. 0.6, I can graph. Now, can it ever touch the x-axis? No. What is the x-axis in this case? No, the x-axis. What is that called? Asymptote. Okay. Then you draw in the shape of the graph, and that is our function. All right, now, domain. Does this ever stop going left? No. Does it ever stop going right? So what is our domain? -infinity to +infinity. Now, our range. What's the lowest y value? What's the biggest? And then everything will get a parentheses. What is our point of our y-intercept? 0, 1. There we go. All right. Now we are going to look at question 5. All right, for question 5, okay, we are going to do the same thing, okay? Now for this question here, what is our B? 3. So is that going to be growth or decay? Growth, okay? Clear what? Get out of the table, click graph clear. All right, so we're gonna go back into our calculator. Let me switch over so I can do this. Okay, now I'm gonna go back to y equals. Now I have an equation there. I don't want to be an equation there, so I'm just gonna clear it. Okay, then I'm gonna do 3 to the power of x minus 1. And once I do that, then I'm going to do second graph to go back to my table. And it still gives me the same thing. Full table. So we're going to use that table to fill in everything else. So from here, what is the value of that table at negative 2?
Negative 0.88.
Okay, so negative 0.89. Okay, what is the value at negative 1?
Negative 0.667.
Yes. Okay, what is the value at 0? Okay, what's the value at 1?
2.
What about at 3?
8.
Okay, I want to do a quick conversation of why this one is at 0. Okay, what is 3 to the 0 power?
0.
What is anything to the 0 power?
Oh, 1.
1. What is 1 minus 1?
0.
0. Okay, that is why it's at 0, not at 1 right there. Yes.
I believe that's 3.
Oopsies. Thank you. Okay, so now, let's go ahead and sketch this in. So we go to negative 2, negative 0.89. So that's almost a negative 1, but not quite. Negative 1, negative 6.7. So that's almost at a half, but not quite. The 0.00, 1, 2, 2, 8. Now, this time, where is my asymptote this time?
It's at negative 1.
It's at negative 1, okay? We know that because this right here, by saying minus 1, is saying our asymptote is getting moved down 1. So our asymptote is at y equals negative 1. So it can get close to negative 1, but it cannot cross it. Okay, then what would our domain be? Yep. Okay, then what would our range be? And what would our y-intercept be? 0, 0. Okay, then we're good to go ahead and look at the back. Okay, we are going to drop down. Actually, we're not going to drop down. We're going to talk about 2 things for 6 and 7. Then we're going to do 8. Then you're going to do 6 and 7 on your own. I know. Okay, for number 6. Okay, what is our b for number 6? 1/3. Is that going to be a growth or decay function?
Decay.
Okay, what is the asymptote going to be for number 6?
4.
Y equals 4. Okay, because of that plus 4 right there. It gives us asymptote of 4. Now for number 7, okay, number 7 has an A and a B. What is our B? 2. Is that going to be growth or decay?
Growth.
Okay, now is anything being added to the end of this? So where is the asymptote?
0.
Okay, now we're going to do number 8 completely together. Okay, so for number 8, what is our A? 5. What is our B? 1/2. So is it growth or decay? Okay. What is the asymptote going to be? Y equals negative 3. So at negative 3 will be the line we cannot touch. Now, we're going to use a calculator. I'm going to use the other type of calculator, not the graphing calculator this time, to do the table. Okay. So if you have one of these handy, okay, do you see the button that reads table? You click that button, okay, and it will give you a y equals screen. You clear that out, okay, then you're going to type in what the equation is for that. What is the equation for this one? 5 times 1/2, and it gets raised to the power of x. And the x button you use for that is right here at the bottom, right there. Okay, then you press enter, and you go to OK. Just keep pressing enter until it gets to OK, and there's the table. It gives you the full table, and you can scroll through it just like the rest of it.
Where's the
Oh!
calculator?
She literally just said it at the bottom.
It's right there.
It said clear bar. Let me see our calculator. I don't think
Okay.
Oh, I got it.
Okay, and I did forget to do the minus. What do I need to put at the end of this?
-3.
Okay, go all the way to the end, do -3. Press enter until it gets to OK. And there we go. Yeah. So that is the other way to do it. You can use either type of calculator. I do not care which type of calculator. You can do it by hand. I don't care. I just want you to understand where it's coming from. Okay. So now, let's fill in this table. At -2, what's the y value? At -1, what's the y value? At 0, what's the y value?
2.
Okay, at 1, what's the y value? Okay, what is the same? -1/2 is the same as -0.5. Yep. What is the y value at 2?
-7.
Okay, what is 7/4 the same as? 1.75. Okay, so now we're going to graph this. So we go to negative. Can I graph the point -217 on this?
Nope.
Go ahead. Can I graph the point -1.7 though?
Yes.
Can I graph 0, 2?
Yes.
Okay, then we do 1 -1/2. Then I do 2 -1.75. And I can get really close to what line but not touch it? And what is our domain here?
Infinity, -50.
What's our range going to be?
-3 to infinity.
And what's our y-intercept? Okay, so what I want y'all to do is I want you to do the other 2 of these questions, okay, on your own. And then I'll have the answer up here for you to check. Then we have 5 questions in Delta Math, like the first 2 that we did right here, where you write the equation from a table. Okay, so I want you to go in and I want you to do these 2 questions for me. And I'll have the answer up on the board so you can check it. Okay, then you have 5 questions in Delta Math.